When we define the mathematical slope of a line, we are strictly defining its angle of inclination. We are measuring a geometric trajectory. Possessing a specific slope value, say a slope of 2, gives us a direction, but it does not give us a specific line. Look at this Cartesian plane. A single slope value represents an infinite family of parallel lines, all tilted at the exact same angle, filling the grid. To move from geometry to algebra, we must isolate one unique line from that endless stack. Isolating a unique line requires a fixed anchor point. Once placed on the plane, only a single line from that infinite family can pass through it. Our goal is to represent that single line uniquely. We must establish a definite algebraic condition that every coordinate on our chosen line satisfies. The equation of a line functions as a strict mathematical rule that tests whether any random coordinate point belongs to that unique geometry. Here is a Cartesian plane plotting a specific anchor point, 5, 7, with a horizontal line passing perfectly through it. The geometric characteristic of this horizontal line is its fixed distance from the x-axis. Sampling arbitrary points, -2, 7, 0, 7, 10, 7, reveals a clear pattern. The x value stretches infinitely, but the y value is locked. That lock yields our first algebraic condition. For this specific horizontal line, y equals 7. Every point with coordinates x, 7 satisfies this condition. We can pivot to the opposite extreme, a vertical line passing through that exact same anchor point, 5, 7. This vertical line is parallel to the y-axis. With an angle of inclination at exactly 90 degrees, its geometric slope is mathematically undefined. Analyzing arbitrary coordinates, we see the inverse pattern. The y value varies infinitely, but the distance from the y-axis remains fixed at x equals 5. The algebraic condition for this vertical line is simply x equals 5. For lines parallel to the axes, the algebraic equation is derived by strictly locking a single coordinate to a constant mathematical value. Deriving equations for non-vertical lines is more complex, as the x and y variables change simultaneously along a trajectory. Consider this line on the coordinate plane. Our fixed anchor point P is at 5, 6, with a defined slope of -2. We introduce a conceptual tool, a floating arbitrary point Q at x, y, representing any possible point on this trajectory. We apply the standard formula for calculating slope, the change in y divided by the change in x. Because Q and P reside on the same straight line, the geometric slope between them must equal our known slope of -2. Substituting our points P and Q into that formula gives us -2 equals y minus 6 over x minus 5. Multiplying both sides by the denominator isolates the y terms. This specific algebraic arrangement is universally applicable. Distributing the -2 and combining the constant values simplifies the equation into its final, clean form, y equals 16 minus 2x. We can test this algebraic condition by choosing a new x-coordinate. For x equals 3, the equation dictates a specific y value. Plugging in 3 for x yields a y value of 10. The coordinate 3, 10 rests perfectly on our geometric line. Setting the geometric truth of a constant slope equal to our arbitrary variables establishes the specific algebraic constraints that define the line. We can also build an algebraic constraint when we are given two fixed points but no stated slope. Consider fixed point P at 5, 10 and fixed point Q at -4, -2. We place a third, completely arbitrary point R with coordinates x, y on this same line. These 3 points are collinear. Because P, Q, and R exist on the same straight path, their slopes relative to each other are identical. First, we calculate the slope ratio between the fixed point P and the arbitrary point R. We calculate the slope for P and Q. To satisfy collinearity, we set these independent ratios equal. The ratio for P to R, y minus 10 over x minus 5, equals the ratio for P to Q, -2 minus 10 over -4 minus 5. Solving the numerical side of that ratio yields a slope of 4 over 3. Rearranging the terms gives us the final constraint, 3y equals 4x plus 10. The sheer geometric alignment of these 3 collinear points mathematically guarantees that the slope ratio remains an unbroken, invariant rule. We have built three distinct mathematical forms: the axis-parallel constants, the point-slope form, and the two-point form. A single structural element links these formulas together. Those variables, x and y, represent the arbitrary point. They are the universal testing mechanism. Regardless of which formula is used, they all perform the same job. They determine if a coordinate point satisfies the geometric realities of the line. These formulas are all rearrangements of the slope definition. Every algebraic equation serves as a definitive constraint born strictly from geometric axioms.